What you could do is say, hey, what if I just measure the position over here with the momentum over here?
Yeah, exactly.
Because those two, you never said, you didn't, you know what I mean? Yes. That's what's happening.
Yes. The idea here is how can quantum entanglement revolutionize measurement precision?
Yeah.
And that appears to be what we have going on here.
Yes. Measurement precision is very big in physics. Physicists love to measure things extremely precisely. The fundamental limit when it comes to actually recording something is really the Heisenberg uncertainty limit, right? This is the limit of the universe. You can't go beyond this just because of the nature of quantum mechanics and the nature of our reality, right? For example, the standard one that you think about is momentum and position, right? If I know my position really well, then I don't know my momentum that well, and so on and so forth, because the product of these two numbers, if one number is small, the other has to be big, such that the product remains about the same. What you could do is exactly what I said. If I really want to know my position very, very well, I could not care about my momentum. I could squeeze my observation such that my delta on one axis is very big and my delta on another axis is really small. So instead of a circle where the error in my, let's say X and Y, these are two different observables, is the same, my error on X could be really small, that could be my position. And my error on the y-axis, which is my momentum, could be very big because maybe I don't care. The challenge is there's incompatibility between different observations. Heisenberg says you can't measure both at the same time. What if I want to measure at two different spots in space? What you can do is instead use entanglement. This is your quantum action at a distance, spooky action at a distance, right? This won the Nobel Prize a few years back in physics. We always use Alice and Bob for these experiments. You send one particle to Alice, you send the other particle to Bob, and then you ask one of them to measure their particle, and that's immediately going to affect, in some sense, the measurement that Alice has, okay? Because these two particles, because they're entangled, they're connected to each other across space and time through some weird mechanism that's like kind of faster than the speed of light, but like not really, but there's nuances. And what these guys figured is, well, actually, what we could do is maybe use this to then up our game in terms of measuring different things at different locations.
Because of the Heisenberg uncertainty principle, we can't know two observable states with high precision. And this has sort of been the boogeyman that everyone's been trying to work around. And this appears to be a very clever way to hijack the limitations using quantum entanglement.
Yes, and that multiple parameter is what's interesting, right?
Right.
Because